Good afternoon, everyone. Today I present to you my presentation on the impact of oceanic acidification in Antarctic marines. First, the introduction. Today I will present to you a critical synthesis of research that I have done assessing the impact of anthropogenic carbon dioxide on our oceans, focusing particularly on the Antarctic's marine life. Our oceans have absorbed a huge amount of carbon dioxide emissions, leading to notable shifts in seawater carbonate chemistry and a concerning reduction in pH levels. I will also talk about the importance of Antarctic marine ecosystem and why ocean acidification is an urgent issue that we need to address right now and right here. So first of all, let's talk about the plight of polar waters. Polar waters, characterized by their naturally low levels of calcium carbonate and reduced buffering capacity, face an amplified risk of acidification. This risk is facilitated by carbon dioxide's increased solubility in frigid temperatures of these regions, shown from the graph on the bottom here, where we can see that lower temperatures has a higher carbon dioxide solubility. And also, factors like high upwelling rates bring carbon dioxide rich waters to the surface. Then we'll talk about the Antarctic's ecosystem at the crossroads. The organisms inhabiting the Southern Ocean and the adjacent Antarctic waters are thus on the precipice of enduring potentially detrimental pH and calcium carbonate conditions. As we speak, the pH of Southern Ocean surface waters has already decreased by approximately 0.1 units, and projections suggest a further decline by about 0.3 units by the year 2100 under the business as usual scenario, leading to carbon dioxide levels exceeding 1,000 mu atmospheric pressure. Next, we'll talk about predictions and concerns for the future. Comparisons across latitudes bring the issue into a sharper relief. While the Antarctic confronts an immediate crisis, studies show that low latitudes waters are also not immune. A drop in pH in the pre-industrial levels of 8.17 to 7.77 is on the horizon by 2100, corresponding to carbon dioxide concentrations nearing 930 mu atmospheric pressure, as delineated by Harton et al. In 2016. As we examine the Antarctic waters, we find a stark warning in the chemistry of the sea. The IPCC's RCP 8.5 scenario, which is a pathway of continued high emissions, predicts that the surface water carbon dioxide levels will surge beyond 1,000 mu atmospheric pressure by 2100, and this is just not a number. It is a threshold that could alter the very foundation of marine life as we know it. The predictions stretch out before us, and a roadmap to the future we must avoid. Models incorporating seasonal carbon dioxide cycles paint a worrying picture. By 2100, winter surface waters south of the 60th parallel may breach the 1,000 mu atmospheric pressure mark. This underscores a nonlinear trajectory of ocean acidification, and actually exponential one, and its far-reaching implications can be shown in graphs in the graph below. Then I'll talk about a meta-analysis conducted by Hancock et al., and they have collected and scrutinized data from a lot of studies, allowing us to synthesize a broader understanding. Through this lens, we see patterns emerge, which paints a global picture of the masses of localized research. The synthesis is really important in its findings, as it shows that acidification is not a looming specter, it is actually present reality, which alters the life cycles and behaviors of marine species shown in the graph on the left. The evidence is clear in the stunted growth of shellfish, disruptive spawning of fish, and the shifting distribution of plankton. After talking about the research, we'll briefly discuss the role of calcification and how ocean acidification actually impacts the calcium organism through this reaction. Calcification is the process central to the survival of many marine species and is faltering under the weight of increased acidity. And here we can see from the graph, when carbon dioxide is absorbed by the ocean, it combines with water to first form carbonic acid. Then the carbonic acid dissociates into a hydrogen ion and bicarbonate. And hydrogen ion actually leads to the increased acidification. And then we'll talk about how the bicarbonate actually dissociates again and forms another hydrogen ion and also forms a carbonate ion. And the carbonate ion combines with the calcium to form calcium carbonate. And with the extra hydrogen ions around, the equilibrium reactions on the left uh, uh, actually shifted towards bicarbonate. And this means that calcium are actually being forced to react and not be available for use for calcium dependent organisms such as coral and sea urchin. And carbonic acid is being formed as a result. And carbonic acid is decreasing the pH of the ocean. And this happens because the excess hydrogen ions tend to combine with carbonate to form bicarbonate. Usually, without carbon dioxide being absorbed and dissolved in the ocean, the graph flows downwards and forms calcium carbonate, which helps the coral and sea urchin build their bones and shells. However, with this negative effect of excess carbon dioxide, the equilibrium shifts to where the graph flows upwards, leading to excess formation of carbonic acid, which is the main contributor to the ocean acidification that we've been talking about. Last but not least, we'll talk about conclusions from the data. The data leads us to a conclusion that is as certain as it is somber. The Antarctic marine ecosystem is at the crossroads, faced with a chemical upheaval that could irreversibly alter its character. And the richness and diversity of the biosphere that have thrived for a millennia are now at risk because of this ocean acidification. And this implication of our findings extend beyond the realm of academics and into the urgent area of conservation and policy. And the scientific community's consensus is clear, and that mitigative action is overdue. And uh, we must reduce our anthropogenic carbon emissions, and we need to enhance conservation efforts and fortify international agreements in order to save the oceans from the carbon dioxide. And as we stand on the frontier of change, the path forward is actually bright because we have the possible tools and we have the power to actually stop this from being more aggravated. And then we have to act with the conviction that our future of our planet depends on the choices we make today. Thank you very much for watching, and this is my presentation about ocean acidification.